Okay, good afternoon, everyone. Today is May the 6th. Welcome to IME 765 class. So in today's class, let's first finish the K-means clustering. Let me share my screen and okay. So first of all, let me annotate here. Okay, first of all, let's go here. So we have finished the introductions about the K-means clusterings, and also the concept of clustering, then the general model of the clustering, ILP model, integer linear program models for in general clustering problem, and also we've showed what we've showed the integer programs for the K-means cluster. Okay, be careful. This is not linear. This is just the integer program. This is clearly nonlinear because you have this one the zk here. Your z is what? Your z is decision variable. See this part? So this is clearly nonlinear. And I've already showed that by doing the trick like this way, and this one is actually somewhat equivalent to the general K-means clustering. It's kind of like a very natural extension when the dissimilarity measure is of two means, of two norms. And the difference here that you have this part actually, okay? However, this can be easily linearized. Why? Because ZLK is a linear model. Sorry, ZLK is binary, and the delta IJK is also binary. Delta IJK actually means delta IK times delta JK. So the multiplications of binary is of course binary. So this is easy to be linearized, okay? And then today let's introduce something else, which is called, which is called K-means algorithm. So K-means algorithm is proposed specifically to solve the K-means, actually use the term to estimate the K-means clustering problem. Again, recall what is K-means clustering problem. For a given D equals to 2 norm, okay, the Euclidean norm, what we're gonna do is that for the given n data and observations, we wanna what? Cluster them into 2 groups, right? And that is the K-means clustering, okay? So the K-means algorithm, the detailed algorithm, the pseudocode actually is given here. In description, it is only 2 steps. Initially, of course, we need to randomly select 2 points to start. And be very careful here. When I said select 2 points, they don't have to be, they do not have to be the data. You know what I mean? You can just, because here we're in the RP space, you can randomly take any K points. Even if these points are never observed, it doesn't matter. You can start with them, it doesn't matter. So initially we choose K points as the centroid of the K clusters. However, in most cases, what we do is that we're gonna choose what? We're gonna choose K observations as my initial centroid. Abdullah, you still remember about another method? Hello? You are muted. If you want to talk, please unmute yourself.
Yep.
You still remember another method?
For K-means algorithm?
For the initialization.
First,
initialization.
The K random points, then select the closest, for all points, select the closest points to K points.
No, I'm asking for the initialization. You are talking about the pseudo methods, pseudo codes of K-means algorithm. I'm talking about the initialization. It is in your report, which you gave me in 2018, I believe, November, December. At the time, I asked you to write a report before you going back. I asked you to write a report for the K-means clustering, for especially for the K-means algorithm, and there you showed the other method. You can try to find your report by yourself. And which is true. Because of that, I noticed that part, and I did a little research about that. But unfortunately, you've already forgot. Anyway, I still remember it. So that's another method, is that in the very beginning, I try to partition it to several parts. However, be careful, that method is not as robust as the method here. Say we randomly choose K points, or we randomly choose K observations. Be careful, again, here points do not have to be observations, okay? They can be any points. Okay, now after the initialization, I have already had the K centroids of the K clusters, right? Then we're gonna do iteratively do two steps. Step number one is that for each data of the
Yeah,
M data.
I have one question.
Yes.
Yeah, because it's look like that for this kind of clustering, initial point is actually very important.
Yes.
Like, so that if we choose the 2.42 cluster, initial point is very close. That means we may get the overlap. So is there any
No, Arap, no worry. I know what you mean. First of all, your first sentence conclusion is absolutely correct. And the truth is that K-means clustering, the initial point, if you choose different initial points, the final results could be very different.
Yes.
You're correct, first. But regarding your second point, that what if I choose initial points very close? You are going to see the examples. It doesn't matter. No, sorry, I should not say it doesn't matter. What I should say is that the algorithm can somewhat correct it by itself. You know what I mean? It doesn't matter what I mean that it can correct. I didn't mean that it's gonna be perfectly fixed. No, it can somewhat correct itself if you choose it relatively close. Because why? Because when you're moving, later, actually the ones from Wikipedia, I'm gonna show you an animation. I hope I can add animation in PDF. Of course you cannot. So I have to give you a link, and then you're gonna see what does K-means algorithm really do. This is one of the most. I guess I can delete one off. This is probably the most famous algorithm in clustering. I'm not saying this is the best, okay, but it's too famous. One reason because this is a special type, a variant of the EM algorithm. Actually, have you heard of EM algorithm before? Expectation maximization. Abdullah or Mahbooba, one of you, I remember, asked you to investigate K-means. So sorry, EM, one of you. I think Abdullah at the time. EM algorithm is too famous. Like for Arab, have you heard of EM algorithm in another course? Due to time limit, I don't have time to introduce the EM algorithm. The proof of EM algorithm itself is a history. Super beautiful. Anyway, we're kind of too far. Let's go back to the problem. So that for the K-means algorithm, the first step, we are gonna, for each data, we're gonna assign the data to the cluster whose centroid is closest to this data. So initially, I've already had K clusters, K centroids, right? And then for each of these N data, I'm gonna see, okay, which one is the closest? Whoever is closest, I'm gonna assign this data to that cluster. Okay. The second step, after assigning all these N data to the clusters, now we're gonna update the centroids of the clusters. That for each data, each cluster, I'm gonna recalculate, okay, what is the new centroid? And then we're gonna go back to one, repeat it. You know, for each data, I'm gonna reassign where is the new cluster, and then after step 2, that is recalculate or update the centroid, and then update the number, update centroid, just repeat. Do it until when? Until cluster, in one iteration, the clustering assignments do not change. If it do not change anymore, then you stop.
Yeah, Dr. Shu. Yeah, in algorithm, is the second for loop is inside the first for loop or not?
Sorry, EM algorithm is what?
No, I'm okay. So are you describing this algorithm 1, right?
Yes, I'm talking about algorithm 1.
Yeah, so in algorithm 1 is the second for loop, the for which k is 1 to k is inside of the first for loop I equal 1 to n, because for after inserting the one new data in a new cluster, we need to update the centroid, right?
No, be careful. No, not. This algorithm is not wrong. Be careful, not. You need to finish the first for loop. What I mean is this. Look at here. You need to finish this. Okay? Assigning all the data. After assigning all the data, then you update the centroid. Rather than you put one data, immediately update the centroid. No. Otherwise, you may have some problem if you do it in that way. I know what I mean. No, the truth is not. You need to finish all this n data assignment, then you update the cluster centroids. Be careful. Okay, there are two different things. That's why I didn't put it here. And another thing, don't forget here's I from 1 to n, and here's k from 1 to k. You know, okay, they're different. And because of that, your question is a very good question, because that's why I wrote it here. See this sentence? If you refer to textbook, most textbooks or online things, they don't have this sentence, because their description is kind of like confusing. They usually say, okay, assign to cluster, then we updated the centroid. Then the question immediately is, then means when? Means you're the one that you mentioned that after assigning, I immediately update the centroid, or the one I mentioned here that I have 2 fors. After finishing the first for loop, I do the second for loop. And the truth is that it's this case, that after assigning all data, then you update. Yeah, this is confirmed, no worry. This is a good question, because at that time when I firstly saw it similar, I had the same question, to be honest. Any other questions? No? Okay, first of all, to let you know, this is a type or a variant of the EM algorithm. Regarding EM algorithm, I think ESL, the textbook have a very good like description about the EM algorithm. And if I remember correctly, I don't know which year, several years ago, I read one article about EM algorithm, and great. It showed the motivation and how people thought of it greatly. If I can find it, I'm gonna upload it to the BB. I don't think I can find it. It was many years ago, because you know, probably you want to know how did the people think of that, rather than just see the answer. You know what I mean? Because just see the answer is kind of really boring. You want to try to really get it. And the steps are very, very similar to this k-means clustering. This unsupervised learning algorithm, it's very, very close. And we have E step and M step. You know, in E step we do expectation. In M step we're gonna maximize the expectation. And that's one of the most beautiful algorithm ever in statistics. It's really, really great, but it's, you know, it's not that easy, especially the proof. It took so many decades for people to finish the proof. Actually, 50 years about. So, and Jeff Wu in 1979, because he proved this algorithm, he got a big prize in statistics. Anyway, so this is about the detailed algorithms you can see here. But here I want to show you something interesting. First of all, let me show you a picture here. So, so look at part A. Part A, this is the original data. Here it doesn't have any color. So initially I randomly, you know, start from 3 points. This is, you know, these 3 points. Okay, 3 points indicating the centroid, initial centroid of the 3 clusters. Okay, and you can see these 3 points are not really data. There's no data here. You see. So who cares? I just randomly start from 3 points. Okay, now picture B is a state that, well, I'm gonna do step 1, which is I'm gonna calculate for each observation. I'm gonna see which cluster is the closest, which centroid of the cluster is the closest, and then I'm gonna attribute all this data to that cluster. Okay, that's why I have the red. You know, this is the red cluster, and all these points are red because they're closest to this one. These are green, and this are blue. Very clear, right? Okay. Now in step C is what? Updating the centroid of the clusters. You can clearly see, for example, in the beginning, the red cluster is here. The centroid of the red cluster is here, and here I updated here. See it? It's moved. And this white triangle means what? It means the previous centroid. Okay. And similar for the green and the blue. And okay, you can see they're moved. Okay. Now what shall I do? Now I have this one, right? And now I have this one. Sorry. And then I'm gonna what? Update the data again. I'm gonna see, okay, which centroid of the cluster is the closest to me. And then you can see, for example, this part, let me draw it. Let me use whatever. Let's use purple color. Let's say you can see this part. It's still green here, but now here, look, they're red. See, so red took over. And also this part, it was blue, and now it's also red. See it? And that's the update. Okay, now I have this. What I'm gonna do is that I'm gonna update again. So previously, this centroid, the centroid of the red clusters here. Now, after I have the new red points, I update It's step number 2 again, the centroid. Okay, it comes here. For the green comes here, and the blue comes here. And now I updated the points again. And this time probably it's stable, so that I stop. Get a point? So what I do is just iteratively, update, update, update. That's it. Get a point? So update the points to the clusters and then update the centroid. Points, cluster, and then centroid until it stops. And the question, how to prove this is convergent? First of all, somewhat, the point, it depends on the definition of convergent. For me, I prefer a tight kind of, or a more strict definition of convergent, which means it's gonna be stable. It's not gonna have cycle. You know what I mean? It's gonna be convergent to one point, and it's gonna be stable. And another definition of convergent that as long as somewhat they're the same actually, as long as some objective value is not increasing, it's going to be smaller and smaller and smaller, then it's going to be convergent. Be careful, the reason this somewhat is not strict is because you may convergent to a very, very terrible point, which is very, very bad. Somewhat it's local point, yes, it's very bad, but you're going to stop there. It's going to be. But for this k-means cluster, k-means algorithm, clearly, in terms of the first definition, it's convergent. Why? Because if you let me see, if you have a look at using k-means clustering using this system, you're gonna see that actually this is something doing in each step. One step I'm doing for this level of minimization, the other step I'm doing for this level of optimization. I'm doing 2 levels of minimizations, you know what I mean? So one min, I make it to be min. And for sure, in each iteration, both objective functions will be non-increasing. I would say either the same or decreasing. And that's why it's going to be convergent. However, this algorithm does not guarantee the global optimal. And usually it's suboptimal to local points. But the good point is that it's relatively faster, much faster than, for example, if you try to solve this kind of things for big N, okay, for big N, big data points. So that in practical, people really use this algorithm rather than, brutally solve the exact solution of a integer program. However, as I mentioned, probably for this problem, if you can formulate it in this way, or for example, if you even delete this ZLK, the summation of the ZLK here, then you can easily get some two approximation algorithm. And then this, with factor 2. So for this algorithm, it's polynomial, and then if you want to compare this algorithm with the k-means algorithm, I don't know. At least I've never seen report like which one in general is better. In some cases, maybe this is better. In some cases, maybe the approximation algorithm is better. So that is the case. And now let me also show you an animation. Yes.
Dr. Xu, I have a question.
Yes. Who's talking? Arap or Mahbuba, right? Okay.
Yes. So
yes.
As you are saying, like the convergent of this k-means algorithm.
Mm-hmm.
So are you saying convergence with respect to initial k-centroids?
No, convergent here, what I mean is that it's gonna stop. It's not gonna jump forever. You know what I mean? No. Strictly actually.
My point is like, depending on initial k-centroids, convergence.
They're gonna converge to different points.
Yes.
Yes. So they're gonna converge to different points. You're absolutely correct. Here, strictly the convergent means this. Let me here. Where's my k-means constraint? It means this. This problem under this system or equivalent to, you can use this, no difference. After iterations, after each iteration, the objective function is going to be smaller and smaller, at least a non-increasing. So it could be the same. Once it is exactly the same, then we stop. However, be careful. Strictly, there are 2 different concepts. Strictly, okay. Why? Because strictly, there's a possibility that you have 2 different assignments, and this objective function is exactly the same. Strictly, it's possible, but it's just like it is just like you buy a lottery. You know what I mean? In general, in real practical, that is almost impossible because you may have thousands, millions of the nodes, and the two objective functions, the measure are exactly the same. You think about the probability, and it's even lower than buying a lottery. You're getting, let's say, 5 million on lottery, you know. So we can almost think that they're equivalent. That once it is, you know, the objective function stop decreasing, we can assume that in most cases it's safe. We can assume that the assignments are fixed. So that is the definition of the convergence here. This is much easier than the general k-means class. Than the general EM algorithm. The general EM algorithm, because this idea is very easy to be thought, but the proof wasn't finished after about how many years? If I remember, about 50 years, because I clearly remember Jeff Wu, who proved the k-means algorithm in 1979. Why? Because I met him and I asked him, how did you make it? He said, oh, that's not too difficult. You just think about it. Oh, okay, not difficult, great. That's why only he did it, not difficult. Anyway, that's why I remember it very clearly. But regarding when was the k-means algorithm firstly proposed, I forgot. Maybe about if I remember correctly, it was 1936 or 1930, like before the World War II, if I remember correctly. Till 1979, people proved it. Do you believe it? There are so many great mathematicians and statisticians. It cost us 50 years. So that thing is really not simple. This is much simpler. That's why I would like to use special case. Strictly, it should be variant rather special case. You know. Okay. Now, do you have any questions, by the way? No. Okay. Now let's see an animation. Arab, Arab, are you here? Hello? He's gone. Anyway, so okay, you're still here. Look at this animation. This can somewhat answer your question. See this animation? Iteration 1, iteration 2, see it? So the centroid is updating, see it? And then updating, and what? Oops, and what? The data, the cluster, the assignment of the clusters of the data, they're also updating, see it? And this is actually the boundary. That is what k-means clustering doing. See it? Okay, so this animation shows some very good points. And after it, let me, come on. Oh, okay, whatever. Let me close it. Is that clear? I need to close it. Otherwise, you know, the JavaScript is running and it's gonna make my system very slow. Okay, let me close it. Okay, then you may ask, so what, where's my, okay. So what are the applications? It looks fun, but what are the real cases, applications of this, right? Okay, the very first thing of it is image segmentation. So image segmentation is that, for example, I give you this picture and I can take this object out and make it black and white. So this is somewhat to strengthen some part of an image. You may ask me, so what is the point? Point number one is that consider, for example, in this kind of medical scan, let's say MRI scan, something, brain scan, right? And it can greatly strengthen many things and make it very strong. Let me show it. MRI scan image segmentation. Okay. So for example, let's this one looks correct. Look at this one. Can you see my screen clearly? Okay, clearly this patient has something wrong here. And let's see this one. Yeah, this one is easier. Get a point? This is the image segmentation. This is very good. Thank you. Let me save it. I'm gonna add this one. I'm gonna update it to my lecture notes. This is I tried to find it, but I cannot. And this is very clear image segmentation. Why? Because if suppose you're kind of very tired already, maybe just have 1 second. I give you 1 second on this picture. You may not be able to see this part. You know what I mean? Especially consider doctors, radiologists, every day they may need to, at least in China, you know, radiologists every day, they may need to read hundreds of this kind of, by their eyes, this kind of film, scan films. They may be tired. But if we can use the machine learning, the clustering technique to make it in this way, everybody can see it. If you cannot see it, I'm afraid, really serious, you need to go to see doctors. If this one, you cannot see it. You know what I mean? So this is very clear. I'm making it to be two main clusters that have only two colors, white. This actually maybe three colors. Actually, you have the gray as well, white, black, gray. And in general, where it is, it's here. In general, my k-means clustering in segmentation is in this way. So consider this picture. This is the original picture. I can store, for example, RGB, you know, red, green, and blue, right? Color, three color here. And what I'm gonna do is that I make the k-means clustering in these R3 features. So for each of the pixel point, it's composed of the RGB. And then undo the k-means clustering. In other words, for this color, which one is this closest to? What I mean is this. Okay, first of all, have a look at a k equals to 2. So the original picture is here. Original picture is here. For example, this one is clearly blue color. And here, it automatically chooses blue and this color, I don't know, 10, looks like 10 color, you know, these two colors. And clearly, this is closer to blue. So all of them are attributed to blue. And then clearly, for example, the kids here is closer to this color. So it becomes to this color, see it? And this, all of these are closer to this. And this part of white color is relatively closer to the blue color. And you can see, this roughly gives you a kid. See it? However, it does, you know, miss some information. For example, the part here. You can see, for example, there's something here, this part. I don't know what is that. Looks like a bone, something. And it's gone here. Why? Because all of them are closer to the blue, so that all of them attribute to blue. See it? However, from this picture, probably you can see there's a person here. You know what I mean? Although from this picture, maybe it's not clear. I mean, this could be an old person, or can be a kid. The face is not that clear. Well, let's use k equal to 3. It's more clear. See it? This is clearly a kid. And you can see, you know, the background more clear. And then if I choose 10, it's even more clear. See it? K means clustering. And as I promised you, I'm gonna play it for my cats. Okay, let's do it. And again, in summer, I'm gonna update all the lecture notes. I'm gonna put my cats there because here I still have to cite this, you know, site because that is from pattern recognition. This is the author's son, very cute. I'm gonna put my cats there. That's my picture and not others' picture. I don't have to cite anymore. Okay, let's see. Okay, first of all, let me show you my cute cats. These are the original pictures. This picture, this one is crazy, and where's the other picture? The other picture, this one is yawning. So okay, now let's do the k-means clustering for them to see what's gonna happen. To see my baby cats will then be tigers. Okay, so what I do here is that I'm gonna first read the picture here, and this means I'm gonna show the picture, and then here means let me use the two means clustering. Okay, now I'm gonna do the two means clustering to this one, and then let's see what's gonna happen. Okay, oops. So here we go. Can you see it very clear? So this is the actually I can use a subplot. Whatever. This is the figure. The left one is the original figure, and this is the two means clustering. And here you can see it automatically chooses purple. I don't know why purple and yellow, the two colors here, and each part is designed this way. Actually, let me see. This is next time I better code it by myself. This is actually I directly use the k-means provided by MATLAB. It's not that clear. I don't believe it is really by the RGB. It may be by some other layers because you can clearly see it's. I mean, strictly it ups. Where are my pictures? Strictly, it has more colors. For example, regarding the purple, this is dark purple. This is shallow purple. You see, it's probably by some different layers rather than RGB. Next time I'm gonna code it. But in general, roughly you can see there are two colors. One is purple, one is yellow. See it? Okay. Now let's see. What if I have more clusters? What's gonna happen? Let's see. For example, let me make it to be, let's say 5. 5 means clustering. Okay. Okay. Oh, great. My cats become tiger. Did you see? Anyway, so this is the 5 means clustering. It becomes like this way. Okay, now let's see. What if I choose, let's say, 50 means clustering? It's going to be very terrible, I guess. It's very slow. Let's wait a little bit. Come on. Am I too smart? Slow? 50 means clustering. Still running. Okay, here. Jesus, I cannot believe it. Which is really bad, unfortunately. So this is probably not a too good example. Okay, next time, let me code it by myself. Directly use the RGB, because here it uses the layers, the color layers. In the research with Nagon, I know something about the color layers. Actually, we have 3 layers. This K-means clustering probably do the clustering in the 3 layers. They combine the feature together. That's why it's not that not to be honest, not as good as the example here in the book. In the book, the author, I guess, coded it by himself and completely use the RGB. Because if you completely use RGB, you should expect that when K is bigger and bigger, it should be more and more clear. You know what I mean? Unfortunately, in my cat's example here, when K becomes bigger and bigger, it's not that clear. This is actually not that clear compared with the original. Where's my original picture? Compared with my original picture, this is not that clear actually. Oh, here you go. This too. Okay, anyway, this is just a conceptual indication of the applications of K-means clustering. So this is something like image segmentation. It's let's still go back to use this picture, this example, which is bigger, which is better. So for example, here you can clearly see parts. This K-means clustering. The kid part and also this face part, these two are strengthened. See it? And also, for example, here, here's not that clear. For example, this K equal to 3, this part is strengthened. So this is something, of course, not as good as this part. This is very, very clear image segmentation. This may greatly help people to capture some important information. In other words, it is trying to describe what is the most different part. Okay, another very important thing is the data storage compression. Why? Or let's say image compression. Why? Think about this. Initially, I have n pixels and I have RGB 3 colors. Okay, so it takes 3n units to store the complete image. Unit here means to store 1 pixel, for example. In most computer systems here, 1 pixel is represented by what? By 1 byte, which is 8 bits, right? So totally you need 3n times 8, which is 24n bits to store this image. N is the number of pixels. Okay, now by comparison, after K-means clustering, what we need to do is that we only need to store this K centroids. And plus for each data, each pixel, I need to store 1 number, which indicates which cluster it belongs to. So totally how many what is my storage size? I need to store 24K, meaning that the centroid, the RGB of the K centroids. So I have 24K plus n times log 2K. Why log 2K? Log 2K means how many bytes, how many bits do you need to store this K? For example, suppose K equal to 8. So you need 3 bits, 1, 0, 0, actually 4 bits. I should say plus 1. It should be plus 1. Log 2K plus 1. So you need 4 bits to store the digit 8. See it? So this part, the floor part, log 2K plus 1 is the number of bits needed to store this digital K. And this is for each pixel, so you need n such pixels. So you can clearly compare. Original takes me 24n. The new one takes me 24K plus n log 2K. In real applications, n is much, much, much bigger than k. N is usually million-wise, and k is usually, let's say, 10. See the difference? It's gonna be a huge compression. Of course, however, use this method, the bigger, the better, should be. I mean, if we strictly use the RGB, okay? So here's a trade-off, because the more clusters you have, the more, the closer the picture is gonna be to the original image. However, you're not gonna save so much. If you took K, for example, this is the original one, for example, you choose K equal to 3. You're gonna greatly save the storage. So it's a trade-off, okay? So here are the 2 things for the K means clustering. Any questions? By the way, can you think of a method to detect the parts of a person? Let's say here's eyes, here's nose, here's mouth. Think about it. It's super simple, actually. for this content. Assuming that it's a picture, okay? It's not video. If it's a video, it's very, very difficult. You need to do something about the displacement and the shifting and the rotation the detection. But assuming it's a picture, it's not gonna be moving. It's very easy actually. Okay, so here's everything about the k-means clustering. Any questions? Or if you have further questions, please feel free to contact me because I do have office hours after it. Okay, now let's go to lecture 13, which is PCA. Again, I wish I have more time. A lot of things about machine learning should be introduced here. And indeed, the machine learning things are really, really interesting, amazing, many of them. Okay, let's go to PCA here. First of all, make sure you downloaded the lecture notes. In the very beginning, let's talk about something very interesting. Let me mention one name, Michael Jordan. Who's Michael Jordan? Can anyone give me some description? Use one sentence, very short sentence. Michael Jordan. What, Arab? You don't know who's Michael Jordan? None of you know Michael Jordan? Seriously?
Basketball player?
This guy, you don't know him? None of you know him?
I know. He's a basketball player. Like, I think he died like last month or something.
He died? No, Kobe. You're talking about Kobe Bryant.
Oh, yeah. I'm not so
God,
sure. I don't know.
please.
Yeah, Kobe died.
Kobe Bryant died on January 25th, if I remember. Or 15th or 25th. After. You scared me. He's my favorite.
I'm sorry.
Michael Jordan. Okay, Michael Jordan is the king. Is the king of basketball. Maybe you guys are not a fan of basketball. I mean, if you know something about basketball, everybody knows him. He's the king. Or let's say Michael Tyson. Do you know who's Michael Tyson? No,
Boxer?
Right? Or do you know who's Cristiano Ronaldo or Messi? Messi.
I know
right?
Mike Tyson.
Okay. Okay. Let me ask you. Okay. For Messi, I don't know. Did he go to university? Maybe. Let me ask you this: how many of you know what is the level of his calculus? Is his calculus level good? Do you know it? You don't know it, right? Nobody knows how good his math is in general, not to mention calculus. And then nobody cares. Nobody cares, right? Okay, let's have another example. Isaac Newton. Everybody knows Isaac Newton, okay? If you don't know Isaac Newton, then serious. And another reason because you just saw Isaac Newton. You just saw it, which is right here. This one is Isaac Newton, this crazy cat. I named my cats by scientists. So this is Isaac Newton. This is Maria Curie because she's a female. This is male. So anyway, so if you become famous, one good thing is later you may, your name may still be there as a form of a pet or whatever. Anyway, just a joke. But Isaac Newton, when I mention Isaac Newton, what do you feel? What do you think? What comes to your mind first? Calculus, right? Or Newton's law, right? The three dynamic laws. You probably don't care how good his football or his basketball skill is, right? Have you ever heard, let's say, how good Isaac Newton can play football or can play basketball? Never, right? Okay, then let me ask you, why don't we care about Messi's calculus level? Rather, we care his football level. Why don't we care the football level of Isaac Newton? Rather, we care, for example, his mathematics or physics. Why? Because football is the characteristic of Messi, right? When we see Messi, we just say, okay, football. In terms of other things, he might be the same, very close to us. For example, if you compare his level of linear programming, I'm 99.99% sure that I'm better than him. But regarding football, I'm 100% sure that he's much, much better than me, right? And me, not only me, for most people, he's much, much better than most people, right? So in other words, the football for Messi is his characteristic, right? Okay, the same for Isaac Newton. Who cares how his football is? Regarding football, he may be the same as us, maybe even worse than us, who knows? But regarding physics or mathematics, he's the king. So this kind of science is a characteristic of Isaac Newton, right? Okay, clear? The question is, how many attributes does a person have? A person could have millions, even billions of attributes. Your height, your weight, for example, and many different things. For example, how good your calculus is, how good your operations research is, how good your basketball skill is. You know what I mean? Millions of data. If I want to ask you to describe, let's say, Isaac Newton, would you really tell people, hey, on which day Isaac Newton's height is what, the weight is what? You are not, right? You're just there to tell me, hey, Isaac Newton is a great mathematician and he is the king of the dynamics, right? We're gonna use what we tend to use this kind of characteristics to summarize the data. Am I correct? Clear? Okay. This is the concept of principal components, that I may have many dimensions of the features. I don't care so many. I only need several critical components. Be careful. When I say critical components, it doesn't have to be one feature, or I should say, it doesn't have to be one attribute, okay? It could be a combination of several features. It doesn't matter. But in terms of this, it's a one-dimensional. You know what I mean? In this feature direction, it's one-dimensional. I tend to use several important, or I should say principal components to describe the data. See it? That's a concept of principal component. Okay, now let's go back to the principal component, to the machine learning, let's say. What does that really mean? Okay, suppose we have here n data, each with p attributes. Assume p is a large number, not a very small number. So we say the first principal component is the direction in this RP space at which this n data differ the most. And the kth principal component is the direction in this RP space at which this data differs the kth most. What does that mean? Okay, let's have a look at, let's say, Isaac Newton again. In which direction Isaac Newton is most distinguished from us? Science, right? Physics, mathematics, right? In this direction, he's most different from most regular people. And that's why he's defined in this direction. How about Messi? Same. Football or soccer. He's most different from others. So these are the first principal component. Get the point? And then you probably know, for example, for Isaac Newton, he is somewhat a very good chemist as well. But because there was a surprise, right? But there was a fire, an accident in his office, burned all his, kind of like the book or all his notes about chemistry. So he could not publish this. Actually, his level of chemistry is very good. Have you heard of Newton's most important book? His most famous book that defined him, The Principle of Mathematica, in Latin language. Till now, if you want to read it, please. I do believe, especially for high school students, it's much better than their textbook. Super beautiful. I just read about 2 or 3 chapters at that time. It was a Chinese version. Oh my goodness, you can see how crazy it is. I mean, I can completely understand if a person can write it like this way, he must be a master, a true master. Anyway, so for example, the second principle of Isaac Newton might be chemistry. Just for example, the third one, whatever, I don't know, can be something else. Let's say he's an officer later about, I think he's the one who's actually in charge of the what is this, the department which is responsible for making the currency, to printing the bonds, the money there, and then he was a leader there. Maybe that is a third principle. I don't know too much. In general, is that case that the kth principal component in the direction in this RP space at which the data differs the most, the kth most. Okay, so this is the definition of the principal component. Before giving you a very clear mathematical definition, let me first show you some kind of like the application, or some concepts in terms of application. So first of all, when I say the first important, second important, or the kth important, k is from 1 to p, actually what I'm doing is to reset the coordinates, so that I don't have to consider the original p dimensions. the original, coordinates. I can rotate or can switch these coordinates to be a new system, which is composed of the k principal components. So I want to make it in the data in a way that, here we go. I want to reset the coordinates to express the data more properly. Properly here means the observation can be showed in a way that differ from each other the most. Okay, you may say it's kind of like abstract. What does it really mean? Let me show you an example here. Oops. Okay, full screen. Okay, consider the data here. See this data. This data, originally, it's like this way, right? And we can see what? Actually, if we go this direction, see it? The data is going to be expanded more. Why? Because have a look at this. If you just measure in this way, so what is the total, let's say the width of this? The width is just like this way, see it? Of the data. But if you rotate as these two arrows, you establish the coordinate system in this way, then you see what is the length. The length here is going to be like this. It's clearly longer than this one, see it? It's more expanded. That is the meaning of a proper coordinate system. I expand the original, this is original feature 1, this is original feature 2. I rotate it and then move it, and then such that I expand it in the principal components coordinate system. This is PC1, this is PC2. And this is clearly the data is more different. They expand the most towards this direction. Maybe still not that clear. Let's go to a 3D example. So this is the original 3D. Let me directly run the MATLAB. Otherwise, maybe especially the first figure, it's not that clear, I guess. Let me see. Where's my code? It's here. Okay, let me run it. Okay, here we go. So figure where this is PC. Okay, this is the figure. This is the figure 1. Okay, let's make it bigger, and then let's try to make this. So this is the original data. The original data is kind of like this way. I distribute it as a normal distribution, and I give it kind of like a z function, add a little randomness, so it looks like this way. But if you just see it in this way, this is the original data. See it? And then okay. Because when we plot it, we want to plot it in 2D, right? We cannot plot it in 3D. Okay, so this is original feature 1 versus feature 2. Can you see anything? Not that clear. Original feature 1 versus original feature 3. It's better, but still not that clear. However, it's better. Be careful that here I make the color to be red and blue on purpose, okay? Because I want to let you see that actually when I generated, I manually made them to be kind of like 2 groups. You can see it. If original data, both of them would be one color, let's say black color, you would not really see these 2 colors so clearly. You know what I mean? Imagine both of them are black color. Can really differentiate it very, very well? I doubt. Okay. And this is original feature 2 versus original feature 3. The truth is what, guys? The truth is if I can observe towards this direction, see it? It's very good, right? Because in this case, you see, they are very different. And also, if I go from this direction, also it's very good. Why? Because have a look at this. The distance here is very large. See it? Okay, these are actually our first, second, and third principles, which is given here. I'm not cheating, okay? Because I run it. I just run it. The principal components is like this way. Okay, in the new coordinate system of the principal components, it is here. This is PC1, this one. This is PC2, this is PC3. And it's like this way. And you may say, hey, it's still not that clear, for example, if you have looked at this angle. It's not that clear, right? Okay, no problem. Have a look at the 2D pictures. This is PC1 versus PC2, which is what? Which is, you can see, in this direction, very big difference. See it? They expand very large in this direction. Okay. And I know from our eyes, we like this picture more, the second picture, this one more. Why? Because in terms of classification, it clearly showed you like this way, see it? Remember in LDA, using Fisher discriminant analysis, remember? We did something similar, but be very careful. Again, here we're doing clustering. So theoretically, both of them are black color. You know what I mean? If you are doing classification, of course, you are going to use LDA. Why? Because LDA is a classification tool. And you do have the label, which is blue and red. But here we're doing not clustering. We are doing unsupervised learning. We're doing PCA, that we do not have a teacher to teach us, to tell you this is blue, this is red. Okay, so in terms of PCA, all of them, both of them are the same color. They consider them equal at the same data set. And this immediately shows you something very different. You know what I mean? Actually, by our eyes, if we see something like this way, you may immediately think about clustering and then do classification. You know what I mean? So this is a very, very powerful. By comparison, look at our old ones, our original space. See it? Can you see it very clearly? Look at this. And this is our PCA. You can clearly see the difference, right? Okay, and this is the principal component 2 versus 3. To be honest, 2 versus 3, it's not that good. It's kind of like similar with original feature 1 and 2. However, the truth is that maybe I can only use these pictures to represent the figure. So this is the very first application that we want to find a better coordinate system in along which direction the data would differ the most. Differ means expand the most. The second thing is that PCA is widely used for dimension reduction. So consider this. This is digit 3. So all these pictures are generated by, this is the original one. So here you can, for example, shift it and rotate it, you know what I mean? So that they're gonna have different 3s. This image is 100 by 100 pixel. So if we just store the image, how many dimensions you have? Original space, you need 10,000 pixels, right? 10,000 dimensions to indicate it. Assuming, let's say, each pixel only 2 colors, assuming, for example, black and white. So you need 10,000 pixels. However, actually, here we only have 3 degrees of freedom. They are first displacement or a shift in the horizontal direction. The second one is a shift in the vertical direction. And third one is kind of like a rotation, kind of like this way, rotation. I only need these 3 degrees of freedom. And then plus the original picture, let's say, which is like this, I can already record everything, right? I don't need for each picture to take, let's say, 10,000 pixels. I don't need it. And then later, you're gonna see, after today's class, I'm gonna update it because something more like SVD, I haven't put it here. More things gonna be put there. And using PCA, we can make it to be very, very low dimensions. I can show you a little bit here. We can make it to be this way, actually. Let me see, digit recognition. And the result is here. Original digit. I use only one principal component. This is kind of like 1D. It's already like this way. Ironically, don't you feel like 1D is actually better than 10Ds? Because this is more like a 3, you know? So anyway, and this is 50. This is 250. Although 250 is not a small number, but compared with 10,000, that is too small, don't you think so, right? It's a huge, huge dimension reduction. And it's gonna be done automatically, okay? You don't have to manually control it, automatically. So these are the power of PCA. Okay, so after talking so many things, let's introduce the math a little bit. Due to some time limit, I'm gonna, very, very roughly talk about the math. And you guys need to read step by step very clearly about the math derivations here, okay? First of all, for the notation part, I record the same thing, record x in this way, but again, be careful, each row is an observation, okay? Each row, not each column, each row is an observation. So I write it in this way, x equal to x1t, x, this in terms of the row. Again, if I write an xi vector, it's always a row, a column vector. So x1t is a row vector, which is n by p, the dimension of x. Okay, now what I'm gonna do is that the PCA is actually to find what? To find the direction, for example, the first principal component is to find the direction in this R space, in which direction my data gonna expand the most. What does expand mean? In statistics, what is a common, let's say, measure for expansion? Variance, right? Variance is to measure the dispersion of the data. right? Okay, so we can explain in this way. PCA translated in this. We want to find the first K principal components, namely 3K orthonormal directions in RP. Be careful, RP, feature space, not Rn, okay? Such that after projecting the original N data into these directions, the variance of the new data are maximized. Be very careful here that, especially these three, I have a footnote here. YK orthonormal. Orthonormal is very easy because when we say direction, we always say unit direction. Otherwise, it's kind of meaningless. For example, if the direction, you know, the V direction, the norm is 2. So final line divided by 2. You know, so to make my life easier, I always assume directions are unit direction, which is very easy. But how about the orthogonal part? Orthonormal means orthogonal plus normal, right? How about orthogonal part? Why they must be orthogonal? Conventionally, people directly define it. However, here I have a proof that you don't have to define it. Even if you don't define it, I can prove that it must be orthogonal. It must be correct. Okay, so now let's show it step by step. First, when we say the variance, we want to make it clear because here I have n observations, each with p dimensions. How to calculate the variance? Strictly, again, it should not be called variance. Strictly, it should be called strictly it should be called covariance, actually. Okay, now let's see how can we make it. So in lecture 2, we mentioned that this is the notation. This is the definition of variance, where G is a random vector follows this P. Joint distribution. That I don't know, of course. Okay, so this is a variance. Now let's assume that I have, oops. Now let's assume that I have all this data, x1 to xn, and all of them are RID, follow the distribution here. Okay, first of all, to estimate this expectation of the G, I can use X bar. Again, be very, very careful. X bar is in terms of the nx data, okay? It's not in terms of P, it's in terms of n. So I have n observation. What is the mean observation? I use this one to estimate the mean of that. Okay, now I use this formula. For each x bar, I have what? For each xi, I can estimate the variance in this way. And now for total n observation, I can estimate it in this way. Why? Because for each observation, I assume they are RID, following the same distribution, but they are identically and independently distributed. That's why the variance of them equals to the summation of them. And hence, I can define the variance in this way, okay? So this is the variance formulation in the original coordinate system. Be very careful. The original coordinate system that I give you means you observe it. Let's say, for example, let's say feature 1 is the height of a person. Feature 2 is, for example, the gender. Feature 3 is, for example, the weight. For example, this is your original data space, your original coordinate system. Okay, now let's have a look. Because what I mentioned that PCA is in the direction. Let's say the first principal component is the direction in the RP, such that projecting the original data onto this direction, the variance of the new data will be maximized. In other words, I want to know. Okay, suppose I project the data onto one direction. What would be the variance of the new data, right? Otherwise, how can I do the PCA, right? Okay, now let's have a look how to get the expression of variance of the new data. The new data is constructed by projecting the original data onto a unit direction V. I don't know what is this V, and I want to get this V. Now let's see it. Let me ask you, what is the data? What is the coordinate of projecting a data xi onto V? Very easy. The coordinate of it is directly inner product of xi and V, right? Suppose V is known, okay? Isn't it correct? In other words, this is the coordinate in this direction, in the V direction. What I mean is this. Okay, suppose, let me draw this. Consider, let's say, why it's this direction? Consider, can you see my screen? Consider this one, okay? So this is my original coordinate system. Okay, now for example, I have some points here. Suppose I have a point here. And suppose the coordinate system in this original, call it, for example, x1, x2. No, let me, otherwise you may get confused of x1 here. Let's call it O1, which means it's original one. Okay, original one, original two, O2. This is the data. Suppose in the O1, O2. Okay, let me type. I cannot tolerate it. Too ugly. Original. Suppose, for example, it's called, let's say 3, 6. For example, this is my original coordinate system. Okay. Now I say, hey, I don't like it. I change it to this coordinate system. What's still the same color? Red color. Okay, let me use, let's say, this color. Now my new system in this way. Okay, so the same data point. What is your coordinate? Your coordinate might be new. Might be, for example, 0 and for example 1, right? Okay, but how you get it? Isn't it how you get, for example, the new one here? Why this one 0? You project it onto it. And how about this part? Of course, here you need a shift because you need x1 minus. Sorry. This is kind of not like. Let me. You need to shift it. Let me say this. Suppose this is here. Let me see how can I get a good point here. Let me make a. Can I make a bigger one? Let me use the vector notation. This is kind of like vectors here. And then I want to see what is the direction, what is the coordinate along this direction. Let's say use the red direction along this direction. So what I'm gonna get is this one. Where did? What I'm gonna get is this part from here to here. See it? And I want to have a projection here. See it? So I want to know this length, right? What is this, not length, this coordinate could be negative, okay? Isn't it this one in the product of this one? Suppose this one is a unit direction, right? And hence this is my new coordinate, x inner product of v, which is vtxi. Okay, now I do this for all the i's, isn't it? You know, by this formula, isn't it exactly the same? What I'm gonna do is that I need to change my xi's and x bar to be vt times xi, vt times x bar, right? Okay, and then expand it, I'm gonna have this, where s is defined here. So what I'm doing here is actually nothing, just left and right multiply a v on vt and v. And here, hence, I have vt as v. Something is worth mentioning here is that because here v is one-dimensional, and hence this number is a scale. This is a scalar. This is a one-dimensional scalar. But here, look how many dimensions I have. I have p by p. Why? Because my coordinate system is a p. I have p coordinates here, p axis here. That's why I have p by p. And here I have only 1, so it's a 1 by 1. Okay. Now let's have a look. According to my definition, what do I have? I want to maximize. I want to find a v to get my first principal, where it is, to get my first principal component. I want to get a v such that this variance is maximized, isn't it? Here should be 1 over n. It doesn't matter because you're going to maximize 1 over n. It's a constant, can be ignored. Here should be 1 over n. So I want to maximize this one such that the norm is v of v is 1 because v is assumed to be unit, right? Okay, Mahabuba and Arab, how do you do it? In LDA, I showed you already, which is nothing but a Rayleigh quotient. Again and again. And I remember at that time who answered the question, I said, how about its minimum? It still be the minimum eigenvalue. Remember? Forget it? Anyway. Okay, just to let you know. That's the Rayleigh quotient. How to prove it? Super simple. I still show the very simple steps. Use the KKT condition, stationarity condition. You know, the derivative of the gradient of this one minus 2 times lambda of the derivative of this one equal to 0. That's it, done. Okay, why minus lambda? Because here's the maximum problem. Minimum problem, you're gonna make a plus lambda. Okay, done. And then you have this. This tells you what? This tells you, be careful, here S is given, okay? Lambda and the V are unknown. Lambda is the Lagrange dual variable and V is the original, the primal variable, okay? So this tells you what? This tells you the lambda and the V must be a corresponding eigenvalue and eigenvectors of S. See it? So, which indicates that because KKT is necessary condition, so it's very clear. And here it doesn't matter because here's quadratic programming. So both necessary and sufficient, it doesn't matter, convex programming. Okay, so it must be an eigenvector V of S. Then the question is which one? Which eigenvector would you choose? Because you have K eigenvectors, right? So what I'm gonna choose is that I'm gonna see what is the objective function look like. The objective function is VT-SV, and we know SV equal to lambda V, right? So actually I have the objective function equal to lambda VTV. VTV is what? VTV, the norm is 1. So VTV equal to 1. So the objective function equal to lambda. So to maximize it, which eigenvalue would you choose? Of course, the maximum eigenvalue, right? And hence V1, which is also the first principal component, where it is? Where's this vector? Hence, the V1, which is also the first principal component of X, must be the eigenvector of S corresponding to the maximum eigenvalue. Okay, so we define this one as the first principal component, and we give it a score for each component. The score is given by the X tilde times V1. X tilde means the centered data given here. Okay, so for each data, I minus the mean. So this is the first principal component. It's worth mentioning that in many different books, including the ESL, oh my goodness, the notations of the definition of first principal components is really, really confusing. They prefer to define this to be the first principal component. Where it is. They prefer to define this one to be a principal component, and they call V1, I forgot a BM, I should have put a BM V1, make it a vector, as the first principal axis or coefficient. Personally, I dislike it. I feel calling V1 as the first principal component is better, and most people actually doing it. Calling V1 as the first principal component and calling this one as a score. And just to let you know, this is just the notation problem. It doesn't matter because all of them use the same way. Get V1 and then get X tilde V. Okay, so we have finished the first principal component. Then how about the second principal component? You may say, okay, easy. Actually, conventionally, people did it, especially when it was firstly invented. People did it. So we just naturally define all principal components are orthonormal. They're orthogonal in the normal. So of course, again, if in this case I use this conclusion, I have what? The second principal component must be the second biggest. Must be the eigenvector corresponding to the second biggest eigenvalue, right? The kth principal component must be the the vector corresponding to the kth biggest eigenvalue here, right? Easy. The question is why you think defining in this way that you define them to be orthogonal as proper. That's why I said, I use cited define. Why you believe that must be proper? And there a way I can naturally get it. Yes, I got it. Actually, here is the proof. The proof is kind of like long, not true, actually very simple. I'm not gonna, clearly introduce it. You guys just read it by yourself, okay? So the point is this. I define this one to be the second tilde. The meaning of this one is actually to eliminate the impact of V1, of the first principle, of the the impact generated from the first principle, which I already know it. So I can just use this one minus this direction. Then in this way, I already eliminate it. Okay, now I do exactly the same thing. For this x2, I try to solve what? I try to solve this problem. Again, we know that, again, by the Raleigh's quotient, the solution of this V, we call it V2, must be the maximum eigenvector of this one, right? By saying maximum eigenvector, what I mean is that the eigenvector corresponding to the maximum eigenvalue must be this one, right? Now let's have a look. What's going to happen here? The truth is that here I want to prove that all eigenvectors of this x2t, x2t tilde t, x2 tilde are the eigenvector. Here I go. I will show that the eigenvectors of these are exactly the eigenvector of this, excluding the first principal component. So if I've already know, okay, all your eigenvectors are the same as S, excluding the first principal component, then let me ask you, what is the biggest eigenvector here? Of course, that's going to be the second biggest one here, right? Because the first biggest one is already excluded. And then you tell me that all of them are exactly the same here. Then of course I'm going to choose the second one. How about the third one? Again, the case one, right here. Now let me show why they're the same. Okay, then you're going to do some very simple operations, this kind of tricky things, and then you know plus because x2 is defined here, and blah blah blah, and finally you're going to have this. Regarding the details, you calculate it by yourself. Again, you must calculate it by your hand. Don't verify it. Calculate it by your hand. Very clear. Okay, now suppose eta is the eigenvector of this, of S actually. What we can show that eta must be an eigenvector of x2 tilde tx. Okay, that means that all the remaining eigenvectors of S must be eigenvectors of x2 tilde x. But still there's a problem. What if I have some more, suppose I have another, let's say called alpha. Suppose alpha is also an eigenvector of x2 tx. And is it possible that alpha is bigger than any of, alpha, the corresponding eigenvalue is greater than or equal to any of this alpha? It's impossible. Because this alpha will never exist. Why? Because have a look here. What's the rank of your x2 x2 tilde? The rank is only p plus 1. And how many such eigenvectors from this s equal to x, how many of these eigenvectors can it already provide you? It can already provide you p minus 1. See it? In other words, it's a full. These are all of its eigenvectors. That's the reason why I only need to choose the biggest eigenvector in the remaining, which means the second biggest eigenvector, again, the eigenvector corresponding to the second biggest eigenvalue of S. I'm done. You know what I mean? So that in this case, yes, my second biggest eigenvector, my second principal component is the second biggest one. How about the case one? Exactly the same. You define the xk tilde in this way. And then you repeat the process here and blah, blah, blah. You try to solve this problem, okay? And it can be shown that the kth principal component must be the eigenvalue of S corresponding to the kth largest eigenvalue. And hence, I have already calculated all the eigenvectors. In other words, all the principal components. Now what we can do is that, what we want to say is here, the new data finally constructed by projecting the original data onto the full principal component coordinates is given by this, x tilde v. V is the columns of all principal components, and x tilde is the shift, is the centered data. Okay, and I can show you my code. My code is exactly the same like this. Where's my code? Let me show you the 2D one, which is easier. No, this is the cat example. Let me see. Where's my is it 2D? Oh, no, this is 3D. Come on, where's my 2D example? My 2D examples here. 2D is here. Okay. So originally I generated the data for fun, and I generate this. All these are not important. The important thing is here. I use XBAR to calculate the mean, and I'm glad that the new MATLAB accepts. You use MATLAB, you probably know this should be an error in older versions of MATLAB. This time it's smarter, they can recognize it. So I don't have to use a for to write a loop anymore. By the way, I'm the newest version, 2019A. If you play it in your version, it doesn't work, so please upgrade it. And yes, you already provide you the newest version. Okay, so now I calculate the PCA of these PCs. You know, I'm lazy, so I directly use the PCA. And in Arab, in your final exam, I can tell you, I will give you some PCA problems there. You are not allowed to do this, okay? You must code by yourself. Unfortunately, you are not allowed, otherwise it's gonna be too simple, okay? And so
Okay,
the thing is here, the thing here is that, yes,
hello?
Yes.
So if I don't, can I use this directly to determine the eigenvalue and eigenvector?
Yes, you're, no worry, I'm gonna write it in the exam. I mean, in the description, I'm gonna write everything there. You're allowed to do this because I don't want you to code the eigenvalue decomposition by yourself. You are allowed to use eigenvalue decomposition to do this. Actually, it's super simple. And you are gonna be asked to do the SVD, singular value decomposition as well. Again, you are not allowed to directly use SVD. It's too simple. Code it by yourself. Anyway, Mabuba is laughing. Lucky you're not formally in this class. Otherwise, you use Python, right? You're gonna use Python as well, and you have to import the library. If unfortunately you don't know which library you're gonna import, your business. Okay, so here, what I do is see here, PC data, which means the data in the coordinate system of the principal components. It equals to x minus x bar times PCs, where x minus x bar is this, is this, smaller, is this one. At this part, x minus x bar is your x tilde here. And the v means the coordinates of all, in other words, v means all principal components. And the v here is my PCs here. My key PCs is PCAX, see, the collection of all principal components as columns. And this means the new data, okay? In other words, the original data, projecting the original data onto the full principal component coordinates. And that's how I generate all these kind of graphs. I can show, for example, I can run it. Let me see where it is, clear it. And this, what is that? This is a PCA. Gee, that's why this is a PCA. So this is it 2D? A 2D, yes, I can run it, I can see. See it? Almost the same as this one. It might be a little different because I didn't make it more beautiful, and also because it's randomly generated. You know, the data are just randomly generated, so it could be a little bit different, but in general, it must be the same. See it? So that's how I get all this. Okay. So in the next class, I'm gonna first introduce the PCA. Sorry, I'm gonna first introduce the SVD, and you are gonna see PCA is nothing but SVD, and the PCA is the greatest application of SVD. And these kind of things are amazing. The reason I put SVD so late here is because this is, after all, not a numerical, you know, course. If this is a course about numerical calculation, I'm gonna put SVD in the very, very beginning. Again,
I have one question.
Yes.
Can I use PCA for regression as dimension reduction technique?
Very smart. And indeed, yes, you can absolutely use it, which is in chapter 3.4. I didn't include it because I haven't introduced the PCA. I personally don't like the authors, you know, put the concepts of PC so early, which is, section 3, chapter 3.5, not 3.4 of this book. If you have the, you know, e-file, you can read it, 3.5. The meaning is exactly the same. Very good question. And yes, you can do it. However, in that case, I have to mention principal components there. I want to keep the content, you know, complete. That's why I put a principal component here. And yes, you can definitely use exactly the same system here that you do a singular value decomposition there, and I take the most important part here outside, and then you select the variables. You know what I mean? However, Arab, you're gonna see this is something very similar to what? Not the same, okay? The similar idea, not the same. In terms of math, they're different. Similar idea to the forward selection. Why? Because in terms of principal component analysis here, you're gonna see the covariance. In other words, which one is the most significant. And that's why it's actually what forward selection. However, it's very good. I mean, very, very smart, brilliant observation. Do it. And let me tell you guys, this the one Arap just mentioned, that is the most important thing in your research, because that's the idea. Math are there as that, you know what I mean? By saying that, what I mean is that everything's there. I didn't invent too much. Most of them are in the book. I may just use my personal understanding to reformulate or have some small tricks or propose some small things. But most of things, it is there. That's it. Ideas are newest. Ideas are the principal components of your research. Ideas sometimes, not sometimes, in most cases can define you. Okay. Okay, that's everything about today's class. And again, sorry for kind of like miscalculating the classes. I do apologize. I really thought that, you know, May 13 was the last class, because I saw in the calendar it shows May 15 as the last class of the semester. I didn't understand that class means actually final exam. Didn't really mean the class. So we will have one more class on the 11th. Okay. Please try your best to attend it. And that's everything about the class here. And it does have a lot of interesting things. By the way, probably you know that the next semester I will have an undergraduate machine learning class as well. So in the undergraduate machine learning class, I will mostly use Python plus MATLAB to do example-based. So if you like example-based machine learning things, it might be good, you know, to audit if you want, if you have time. I forgot the time. Time maybe like every Tuesday, Thursday, something. You can search it. The number of the class is 490. It's listed as seminar because you know, the school has to, you know, do the whole process to approve a course. That's why temporarily it's listed as a seminar. Again, for you guys, make sure that knowledge is the most important thing. It doesn't really matter your GPA, especially later if you want to go to a work. Okay, let me start. First of all, this is everything about today's class. Thank you very much. And let me stop the